general relativity or in quantum mechanics. Apparent contradictions are a consequence of this wrong view of reality that there is a classical world out there.
According to you, particles, space, and even time don't really exist.
The ultimate elements of reality are the Q numbers and not necessarily the existence or non-existence of an atom. That's a mind-blowing conclusion that actually not just particles of light, which are massless like photons, but even bits of matter could actually be created, destroyed. They could exist in this superposition of being created and not created simultaneously. There is a deeper underlying reality which cannot be created and destroyed.
I don't know if I dare open this can of worms, but what about time?
That's also mind-blowing.
Vlatko, thank you for joining us today. Really appreciate it. You've written this book, which is called Portals to a New Reality. And it's really kind of about your vision for the future of physics, isn't it? And
yes.
I've been having a look, and there's some bold stuff in there. You say that this is the list of things that, according to you, don't really exist. Particles, space, and even time. So we're going to kind of dig into that and unpack what you mean by that.
Yes.
I want to start, if it's okay with you, by just talking a little bit about what it means to be a theoretical physicist these days, because some people would have this sort of antiquated idea of you just sort of in a room and writing equations, but is there any truth in that? What are you actually trying to discover, and why do you do what you do?
Yes, I think the question that drives me really, usually the questions are of very fundamental nature, but you have to use your intuition there as to what you think might be a fundamental question that would really change how we think about the basic laws of physics. These are the fundamental questions. You never know in advance, of course, which question might turn out, but you will have an intuition. So going into the areas where you are unifying quantum mechanics and general relativity are two best theories which haven't been unified. Usually questions related to that are considered fundamental and really likely to give us new physics. Whereas, of course, there are many other questions where you are applying general relativity and quantum mechanics, and they are interesting, but they are maybe not interesting for the fundamental purpose.
So I guess you're trying to, I don't want to put words in your mouth, but you're trying to see deeper into the kind of the essence, the base layers of reality. Is that right?
Yes, that's right. You're trying to determine what you think are the fundamental constituents of reality, and then immediately how that impacts our theories and how could one test whether this really is the right way to proceed.
Yeah. Take something like general relativity. It's more than 100 years old now, isn't it? And it's kind of our description of
yes.
space and time. Einstein, of course,
yes.
Came up with it. So in a sense, you might say that we understand space and time, but you're looking for chinks in the armour, gaps where our understanding fails a little bit. Is that so? Maybe give us an example.
Yes, I think that's right. I think that's why you require a certain intuition to approach this, because of course, you know, there is no formal mathematical procedure how to come up with these questions. And actually, as you do come up with them, they may lead you astray. Maybe they are not the right questions to ask, and they turn out to be completely tractable and trivial. So indeed, for instance, if you take general relativity, people observe all sorts of anomalies out there in astrophysics. So when they're looking at motions of galaxies, or when they're looking at black holes and the sizes of black holes, very frequently, one possible interpretation for the deviation is that something might be wrong with general relativity. And that could be the right intuition. Of course, what can also happen is that your observations are not detailed enough. And if you were to do further observations, you would just realize that it's not exactly what you concluded previously, or maybe there are other objects that you missed out in the previous observations, which are the ones that make it appear to be deviating from general relativity. However, if you take them into account, you get no deviation. And I think this exists in both of our fundamental theories, in quantum mechanics as well as in general relativity.
Before we get into talking about that in detail, I wonder if you can just kind of give us a bit of a basic guide to kind of what, because physics kind of has these two central pillars, doesn't it? It's got
Yes.
general relativity,
Yes.
our description of space and time,
Yes.
and then it's got quantum mechanics or quantum physics, our description of the microscopic world of,
Yes.
of particles
Yes.
and interactions.
Yes.
So we're going to kind of break those down a bit in this conversation, and we're going to see where you think the
Yes.
flaws are. But just give us the outline of how we think those two things work in the mainstream at the moment.
Yes, I think they came up, quantum physics and general relativity really came up from two completely different domains, the micro, quantum mechanics, and the macro domain, general relativity. And so the problems that led to the creation and the discovery of these two theories were completely different problems. They had no overlap whatsoever. One set of problems involved in general relativity things like motion of planets. Are there deviations from Newton's laws in these motions? Bending of light was another very big question. How much does light bend when it passes by a massive object? And there was a prediction due to Newton, and there was a different prediction due to Einstein. And none of these problems had to involve any quantum mechanics. In fact, quantum mechanics, if it's relevant at all, the effects are so tiny that we are not really able to measure them at all at present. Quantum mechanics, on the other hand, came from atomic physics. Mm-hmm. People were struggling to understand spectra. When you shine some light on an atom, and the atom answers basically by shining light back, and you detect that, the question is, why do these colors come in a discrete set of frequencies? Why not the full continuum? And that led various people, of course, Max Planck first, then Einstein himself made a fundamental contribution, then Niels Bohr ultimately accounted for atomic spectra in his own model, and that this ultimately led to the birth of proper quantum mechanics. So these were problems where gravity was completely irrelevant. These are tiny objects. The gravitational forces between objects like that even now cannot be measured, actually. They're too small to give you a measurable effect. So you know that you can ignore gravity completely. And if you then fast forward over the last 100 years, both theories have been confirmed. That there's not a single deviation either in general relativity really or in quantum mechanics in any experiment that we've done. But it's still true that none of these experiments probe the common ground between the two theories. So they're really, they have a separate existence, and both are equally valid, if you like, in terms of experiments.
They kind of do different jobs, don't they?
They do completely different jobs.
Yeah.
Yes.
So I guess like the way maybe you can tell me if I'm getting any of this wrong, but as a journalist, I think of general relativity as kind of, it paints space-time as this kind of flexible canvas.
Yes.
It bends, and it's that bending of space-time that creates, if you like, gravity, or just is gravity.
That's it.
And then you've got quantum theory, which is talking about kind of the energy in and out from particles, the interactions of particles and light. And I guess for me, the fundamental point about it is that like the energy levels of particles, we think of them as these fundamental ingredients of reality. And the idea is that they can absorb and release energy in packets. It's not like a continuous thing. It's like they can, little blip comes out and then another little blip comes out.
That's it.
I'm obviously dumbing it down.
Yeah. Yes.
But that's more or less.
That's it.
Right.
That's exactly right. So in many ways, general relativity is still a classical theory according to this logic, because everything is continuous in general relativity. Space and time are continuous numbers, whereas in quantum mechanics, everything somehow becomes discretized ultimately. And I think the first discovery was exactly as you said, that energy only comes in little chunks, the quanta of energy. So both of these theories, they really arose from a completely different set of problems. And the frustrating thing to some degree is that they still continue to exist in exactly the same way.
So I promise we're going to come to your ideas, Vlatko. I think the last thing that we kind of need to set up, because we're going to go on to talk a bit about observers, which has this very particular meaning in physics, doesn't it?
Yes.
Just tell me a bit about what it means in quantum mechanics to talk about an observer. I know you think that it's a bit of a misleading term, but
yes, it's a great point to start, because people frequently say that the trouble with quantum mechanics is that, so the argument would go, is that it requires the existence of observers. So there has to be an ultimate kind of frontier where you detect quantum outcomes. And the people who argue this way would say it's only at that point that things become real. And this is because in quantum mechanics, things can exist in a superposition of many different states. So you can have an atom that exists in two spatial locations at the same time. And quantum mechanics says this state will persist until you somehow engage with this state.
You look at it.
You look at it in some way. Of course, you would involve a lot of experimental apparatus to do that. It would be through some kind of optics elements and things like that. You would amplify it to your computer screen. However, it is as simple as looking at it. And then the question is, you only get one of the two outcomes. And that's what quantum mechanics tells us, that you cannot predict. There's no algorithm to predict which of the two outcomes you will get. It's a random. It's the most random process that we are aware of in the universe. However, beyond that point, the observation solidifies this outcome and you get one of the two outcomes. And some people would say, before you made the measurement, this property of being here or there was not real, it wasn't actual, but you need to ask this question, you need to look at the system to really find out whether it's in one state or another. And
it leads to all these metaphysical questions, doesn't it? Because if you've got a theory which says before you look at something, it's in two places at once, maybe the most successful theory in science, and maybe some people would say it is, but what does that really mean? What constitutes an observer?
Yes.
And that ties people up in knots a bit.
Yes, it does. And I think we've been arguing about it right from the conception of quantum mechanics. I think there was a famous 1927 Solvay conference in Belgium. And basically, this was a conference that involved all of the pioneers of quantum mechanics. Certainly Einstein was there, Niels Bohr was there, Heisenberg, Schrödinger, Dirac, all of these people were there. And in fact, they couldn't agree on how to think about these things. What does it mean to observe something? Why is the behavior different if you were to observe something than if you didn't observe the system? And again, this is a big departure. People argued from classical mechanics, where a particle has a position and a speed independently of whether you look at it or not. So you can detect someone's speed of motion without really slowing them down or speeding them up in classical mechanics. There is no back action, if you like, no knock-on effect there. Whereas in quantum mechanics, you can never avoid that. And that's the key to Heisenberg's uncertainty principle as well. And then various interpretations, in fact, were offered already in 1927. You can see 3 or 4 key different camps into which researchers fell into. And basically, there were the camps that I think maintain the relevance of observers to a different degree. What exactly constitutes an observer? That's the key question.
So let's, after all that preamble, I think we needed to set the scene about it, but let's come on to some of your ideas. I won't even spoil it, but I feel like you've got a bit of a rebellious spirit to all of this stuff about observers. You think that people have been tying themselves in knots a bit unnecessarily. So how do you think about all of this? How do you solve all these confusions about observers?
Yes, I think it's a huge confusion, and it seems to me that quantum mechanics should be no different to other areas of physics as far as observers are concerned. So remember, even in relativity, we talk about observers. Einstein talked about one person observing a moving train and discussed how these two different observers perceive space and time. And of course, relativity is all about how space and time changes depending on your motion. However, ultimately, you realize very quickly in relativity that observers need not be complex systems, and that ultimately any physical object can be thought of as being an observer. So you can have an atom that's moving with respect to another atom. And these two atoms will also tick at different rates if you think of them as atomic clocks. They don't need to be living systems. They don't need to be conscious, aware of anything. The physics itself will do the job for you as far as relativity is concerned. And I think personally that the same logic ought to be applied to quantum mechanics. That sometimes for educational purposes, you could use the word observer. And ultimately, of course, the physicist doing the experiment is the ultimate observer in the laboratory for all practical purposes. But there's no reason to suppose that observers are any different, just like in relativity, to any other physical system. So basically what I maintain and what I write extensively about in my book is that we can understand quantum mechanics by treating everything in the universe on an equal footing, which means atoms, we treat atoms in the quantum mechanical way, and in the same way we treat, let's say, any experimental equipment in your laboratory, any physical or biological observer that may well be there like ourselves, all of that should be treated in exactly the same quantum mechanical way. And then you realize, if you think about it, and that's the big surprise, is that actually there are no problems anymore. All of these things that people discuss under the name the measurement problem, Wigner's friend, Schrödinger's cat, all of the famous quantum paradoxes, apparent paradoxes, actually dissolve. They're no longer there if you think consistently about it.
So that's fine, but there is something going on here, isn't there? Like we do still have a situation where we go from a superposition to a particular outcome.
Yes.
You explain this very nicely in the book. And I think what you think is going on there is, again, we can explain that with an existing paradigm from quantum mechanics, which is entanglement.
That's it.
So entanglement's an idea that confuses people. Explain what entanglement is, and then explain for us what's actually going on so that we don't need observers anymore.
Yes, I think this goes back to Schrödinger himself, really, who I think offered it initially as a paradox. I think the way that original paper in 1935 was written, he said, look, if you think that microscopic systems behave in this weird way, that they can be in many places at the same time, I can easily give you a thought experiment where that kind of weird behavior will now spread and somehow affect everything else around it. And that's the key aspect of this experiment. So basically he said, imagine that there is this atom which has either emitted some energy or not, a particle of light or any other particle. There is an emission. But because it's a quantum event, it's done both of these at the same time. It's emitted something and not emitted it simultaneously in a superposition. Then he said, if it emits a particle, imagine that there is a bottle containing poison, which gets broken by this particle, the poison gets released, and there is a cat, this is the famous Schrödinger's cat, which therefore dies as a result of that. But then he says, but if you follow the logic of quantum mechanics through, then there will be the other branch, which is equally real, where the atom hasn't emitted, the bottle is still intact, the poison is inside, and the cat is alive. And so somehow he said, if you accept a unity of physics, namely that all physical systems couple to all other physical systems, so the atom can couple to the poison, can couple to the cat, anything else that's there, then suddenly it seems that you have to acknowledge that even things like cats could exist in two different states at the same time. And I think at that time he thought that this sounded paradoxical. However, with time, and that's interesting, he evolved, I think, over the next 20 years. He gave lectures, I think, shortly before he died, in the early 50s in Dublin. And I think these lectures, if you read them, they were discovered much later, actually suggest very strongly that he thought that this is what would happen if you were to conduct this experiment. Of course, we're very far still. These are still thought experiments.
Yes, yes.
But what I tried to do in my book is to outline experiments that may be closer to reality, which would still be in the same spirit of what Schrödinger suggested.
Yeah. So, but how does entanglement come into it, Vlatko? Because I think what you are saying in your book is that we should embrace the fact that both realities are true. Right. But you're replacing observation with entanglement, I think, aren't you? So tell me how that
Yes, and
works.
that's the exciting. Maybe again, it's easier to talk about a system like a human being, could be artificial intelligence in the first instance, because maybe easier to conduct this experiment. But you want, instead of a cat, because I guess it's difficult to communicate with cats in a faithful way. We can't get answers easily from them.
Very difficult.
Very difficult, I think. So basically, if you imagine that there is another person inside who simply has to register whether the atom, forget even about the poison, you don't need to make it as dramatic as that. You simply want to know whether the person has observed this atom emitting light or not. Is it a definitive outcome? What this experiment would suggest is that in each of these two branches, this person, whoever is inside the lab, feels that the outcome is definitive. So in one branch, the person will see that the atom has decayed and will simply behave in that way, that they detected that. And in the other branch, the person will simply realize that there is still no detection, and they may, record that observation, communicate it to someone else. And these two branches can actually still, and do according to quantum mechanics, exist simultaneously. However, in each of these branches, each of these observers, if you want to call them as such, feels that they've seen a definitive outcome. So it's very interesting what Schrödinger is telling us there is that there is a relativity involved in quantum mechanics as well, and it's relativity as to what's been observed and what's not been observed.
Yeah.
So there is a person in one branch seeing one definitive outcome, in another branch seeing another definitive outcome. And now we are going down the road of Wigner, where he says, but what about the person outside of the lab who hasn't really communicated with the person inside? According to Schrödinger, this person would be forced to write the full superposition down. They really would not know which of the two branches are actual. And that's what's amazing, that you have three different perspectives. They peacefully coexist. It's all nice and consistent within quantum mechanics. And until the outside person goes inside the lab and asks their friend, which is why it's called Wigner's friend, the outside person simply has to acknowledge that this is an entangled state.
So with Wigner's friend, you have a person inside a lab and they make a quantum measurement. So they work out, has the particle emitted something or not.
That's it.
And they've determined it.
Yes.
And then you have another person outside the lab.
Yes.
It's a sealed lab.
Yes.
They still don't know. So from their point of view, the particle is still in a superposition.
Yes.
So the question that the Wigner's friend paradox raises is which observer is right?
Exactly right.
That's the question,
exactly right. So it seems paradoxical, because you would think that once you've observed something, it ought to become a fact for the whole universe.
Yeah.
If you see the atom has decayed, surely everyone must agree with you that this is the case. However, quantum mechanics suggests exactly opposite to that. And that's the interesting conclusion here.
So that's interesting. But what I want to understand is, how does entanglement come into it?
Entanglement simply captures this state that in one branch you have the person inside the lab see one outcome, and in the other branch, if you like, the word here is they are correlated to a different state of the atom.
Yeah.
And it's exactly this quantum state that describes this kind of correlation, which we call, or Schrödinger introduced this terminology, an entangled state. Yeah. So basically what this tells you, I can describe it a bit more concretely. If you come into the lab, you yourself can either talk to the person to find out what's going on, and because that person is correlated perfectly with the atom, when they tell you, you know that reflects exactly what happened to the atom. Or, and that's the interesting now thing, that you can actually exchange the observer and the observed, and that's the point I make in my book. You can go and see what happened to the atom. And let's say you see the atom has decayed. You know that if you now talk to your friend, the friend must confirm that the atom has decayed. And that's what it means to be entangled. You have two systems, an atom and the inside, the experimental physicist, who are basically in this quantum state where if you understand what happened to one of them, you automatically know what happened to the other one as well.
Yes. So I'm going to summarize it and you tell me if I've got it right, Vlatko. So I think what you're saying is that, we traditionally think of like an observer, and that language conjures up questions about consciousness. It's troublesome. We think about an observer looking at a quantum system, an atom, making a measurement. What we should really think about is not any of that language about consciousness, but it's when we make a measurement, what we're doing is we're becoming entangled with that system. And if you use that lens, any time that two things become entanglement, that's what really matters.
Exactly right. Okay. So in fact, that's where you remove the need for observers. You could now say, why do I need an experimental physicist? Can't I just get another atom to entangle to the first atom? And wouldn't that constitute an equally good observation? And my answer is yes. That's right.
Yeah. So I want to take it one step further. What happens then to the other part of the superposition? Does this interpretation mean that there must be a multiverse of other, because you started to use the words of branches?
Yes, I think you're right. You're right that it goes in the, I think the closest interpretation is certainly many worlds interpretation. The trouble I have with that is that it describes a very extreme possible state of affairs as far as quantum mechanics is concerned. So I think it doesn't quite even though it sounds weird already, it sounds science fiction and mad. In fact, it's not mad enough as far as I'm concerned. And so I think what would be better to say is that there is perhaps only one universe, really. And I think many people do object to many worlds by saying, well, am I now accepting, exponentially many worlds that are created?
You can never test that or whatever.
You can never test that. In fact, probably it's more correct to say there is one universe, but all the objects inside that universe are really quantum mechanical. So you acknowledge that they have this full spectrum of possibilities of existing in many different states at the same time as far as any property that they have is concerned. So they can have many different locations, many different speeds, many different energies at the same time. Anything you can think of exists in this multiplicity.
Let's move on a little bit. We've established that you think that observers is a bit misleading. It's a useful pedagogical tool.
Indeed.
Maybe.
Yes.
But it's unhelpful.
Yes.
Ultimately.
Yes.
And I think, if I've understood what you're saying in the book, I feel like a big theme of the book is let's take quantum mechanics almost at face value.
Yes.
Like it already contains what we need to understand reality.
Yes.
And so we've talked about how that applies to observers. Let's turn to the small matter of particles now, because I think you also have some views about if we really take quantum mechanics at face value, it tells us some interesting things about how we should think about particles. Tell me about that.
Yes, this is also a fascinating story. And I think maybe a good way to talk about it is to is to simply argue against this view that when you make an observation, people say sometimes you've collapsed the superposition, let's say. You collapse one property, it's vanished, and now it has a different property. I think that's, again, unhelpful to think in that way, because I think you didn't really collapse anything. In a way, when you measured the location of a quantum particle, you didn't destroy the quantum property that exists there as a position. It's still there. Dirac called them Q numbers. So these quantum numbers that underpin everything according to this view, they're still there. You can't destroy them any more than you can destroy a position of a classical object. You have a car standing there, or it's moving with certain velocity, you can change the position of the car. You can change the speed at which it moves, but you're not destroying the properties that this object has. And I think we should be thinking about quantum objects in the same way. It's just that the quantum properties have this weird feature that they can exist at the same time. That's why they're Q numbers rather than C, classical numbers.
And just for people who don't know the difference, a classical number just means 5, 11.
That's it.
A quantum number is a table with lots of different ordinary numbers in it. Is that the
that's
picture?
it. Lots of numbers. And actually Heisenberg, that was the first paper really that people agree was the beginning of quantum mechanics. He literally took these classical properties and made them into these tables of classical numbers, into matrices, basically.
Yeah.
And the key thing of these Q numbers, of quantum numbers, is that the order in which you multiply them matters. And that's what's behind Heisenberg's uncertainty. So if you take a position as a Q number and multiply by speed as a Q number, you're not going to necessarily get the same number if you invert this.
Yes.
Whereas classically, of course, 3 times 5 is the same as 5 times 3.
Yeah.
So I think everything should be thought of as being made up of Q numbers. And again, when you observe something, you are not destroying the Q number, but what you are doing is your Q numbers, if you like, are correlating, are entangling themselves to the relevant Q numbers that you measure. So maybe a good picture here, a good analogy would be, imagine you have a die, and there are 6 numbers that you can get. You roll the die. And of course, now you see only one number come up on the surface. But you wouldn't say the other 5 numbers are destroyed. You're just not looking at them. So now I'm thinking of a die as being a representative of a Q number.
Yeah.
And you could say, but if someone is looking from one side, they're going to see a different number. Absolutely.
Okay.
That's exactly this multitude of different perspectives,
That's
like Wigner's friend, that you get in quantum mechanics. And you don't destroy the die. When you see only one number, you know that the other numbers exist. But of course, you need to perform different experiments to possibly then reveal them.
Yeah. So I'm wondering where this takes us then. You're saying that we think about particles, it's a little bit like when we talked about observers. Particles are this thing that we have in our mind. We might think of them as little tiny balls or something, even though we know that's not quite right.
Yes.
But what you're saying is, no, we should actually be thinking about, we should take quantum mechanics seriously. Quantum mechanics talks about these Q numbers.
That's it.
And that is what's real, not the particle per se.
Yes, and that's, I think to me, that's a mind-blowing conclusion, that actually not just particles of light, which are massless like photons, but even bits of matter could actually be created, destroyed. They could exist in this superposition of being created and not created simultaneously. And in that sense, what this reveals really is that there is a deeper underlying reality which cannot be created and destroyed. And these are the Q numbers, but what you are creating ultimately and destroying are particles. And in fact, this is yet another aspect of quantum mechanics that sits very well with relativity, because in relativity we know that we can convert particles into other particles, into energy even. We can convert energy back into particles. So all of these conversions can be accounted for in quantum mechanics precisely because of this Q number-based reality.
So at the beginning of this conversation, you were talking about trying to kind of find problems to work on, that it would be interesting, intractable.
Yes.
I think from your book, at this point where we started to talk about particles and Q numbers, you had some ideas for some new experiments that we could do that might actually reveal, as per the title of your book, a new reality. So
yes.
Can you tell me a bit about the experiments that you have in mind in this area?
Yes, I think that there are many interesting experiments that could be done. One certainly could be the experiment that really shows that particles are not fundamental elements of reality. And to describe it in a very superficial way, but I think it gives you the key, the gist of the idea there, is to make, let's take an atom. If you want to do that with an atom. Of course, you could take a smaller, simpler system, but I think with an atom it would be amazing, because we're all taught that atoms are we start by atoms, they're the fundamental elements, everything is made up of atoms and so on. So if you are able to put an atom in a superposition of being in two different places at the same time, what you now want to really test is that what the ultimate elements of reality are the Q numbers that pertain to each of these locations, and not necessarily the existence or non-existence of an atom in these places. And I think that's why first you need a superposition of an atom, and then you need to execute certain measurements in each of these places. In fact, what you are really testing is the amount of entanglement between these two locations in Schrödinger. Schrödinger would automatically recognize this as an entangled state, because if the particle is not here, then it's sitting over there, and vice versa. So there are two branches of existence. And so these are experiments that would be very similar to what's required to violate Bell's inequalities. Like any standard test of entanglement is basically what you would have to do here. Yeah. And what you would rule out is, if you were to violate Bell's inequalities in this case, if you would really show the quantum property of this,
which would mean that Bell's inequality being a test that shows something is entangled.
That's right. It goes beyond the classical logic. So that would rule out the interpretation where you could say, well, wait a second, is it possible that the atom really is here or not here? It's just that I don't personally know, which is what frequently some people maintain, that it's our lack of knowledge.
Yes.
Otherwise, it's all fine. Things really exist or they don't exist, but it's just that I'm not aware of that. Until I walk into that room, I don't really know. Yes. This one rules this out completely, because it says, no, it's nothing to do with that. If you were to suppose this kind of underlying reality, you could actually not violate Bell's inequalities. These would be hidden variables in the jargon of physics. So you can do a very simple experiment to show that any quantum, it could be light, and actually experiments have been done already with photons of this kind, and they're much easier.
And they showed that you were right in
and they indeed show the violation of Bell's inequalities. With atoms, it's much more challenging. They are really just technologically harder to do, but it seems to me that's one of the experiments that we could be doing.
Yeah. So you're saying that if you've got an atom which is in a superposition, it's in, let's be sort of a little bit hand wavy and say it's in two places at once.
That's it.
So normally physicists wouldn't think, so entanglement would be between two different particles.
Yes.
But what you're talking about is an experiment that would show that this particle that's in two places at once, as it were, is almost entangled with itself, which seems to suggest that it's these Q numbers that represent these two places that are therefore the real thing.
That's it.
Am I getting that
roughly right? Yes, you're getting it completely right.
And how far do you think we are away from that? Is that like, we could do this next week? Is this years away?
I don't think it's years away. I think people who are doing these Bose condensates and cold atoms do have the right technology to do that.
And a Bose condensate is
a Bose condensate is like a collection of sometimes up to 1 billion atoms, which are all cooled down to a ground state, the lowest energy level, and they basically exist in a huge superposition, in a huge quantum mechanical state. And I think with systems of this kind, we could do this experiment.
So we've established that observers don't exist,
yes.
Or at least that's your view.
Yes.
We've established that particles don't exist. We're going to come on to sort of space and time in a moment,
Yes.
but I just want to pause just for a moment before we move on and get you to kind of reflect a little bit, because you started to talk a little bit there about sort of other interpretations of quantum theory. Some people embrace the kind of observer thing a lot more. They go the opposite direction from you, and they say quantum theory just tells us about our knowledge. It's not a description of reality that out there. It just tells us what we know about reality, a subtle distinction. I guess I want to kind of get you to reflect, like, how radical are these ideas that you're... would people generally accept them? What do you think?
I think they are considered less and less radical now. Certainly 20, 30 years ago, I think they would be considered very radical. And you're right that the Copenhagen view, which is it still is the predominant view, I think, of quantum mechanics, would probably advocate a very special place for an observer. And not only that, they would insist that this observer must be a classical system. And I think that's the distinction that I'm arguing
something the size of a macro world.
A macro world, and that means that when they see an outcome, it's definitely like that. It's everywhere like that. And in fact, I'm arguing precisely the opposite way, that all the apparent paradoxes that we think might be related to quantum mechanics come from the fact that we are introducing this double standard, if you like. We are saying, look, this small part of the universe is really quantum, but when we engage from the outside, suddenly everything becomes classical. And actually, even mathematically speaking, it's very difficult to put classical and quantum equations together in a consistent... I think all our apparent contradictions simply are a consequence of this wrong view of reality, that there is a classical world out there, ultimately.
We've ticked off observers, they don't exist, you say. Particles also, we need to think instead about quantum numbers, that's what you're saying. So we're going to talk a bit more about, like, the future of physics, but before we do, I want to just sort of tick off space and time as well. You know, the minor matter of space and time. I think you feel that space and time also is more of a pedagogical tool than something real.
Yes, I have an argument. Again, this goes nicely back to what we discussed in terms of the problems that you try to focus on as a theoretical physicist. You are thinking, where do I think is something that's really genuinely problematic, and it's going to give me something fruitful that goes beyond what we expect. And of course, no one ever knows. All of these experiments that we're discussing could always go the other way.
You could be wrong.
I could be wrong easily. I could easily be wrong. And actually, that's part of the excitement, is when you notice that there is a controversy. One of the indicators whether you're thinking about the right problems is a huge disagreement in the community. That always tells you that this is interesting. It's unresolved, and it should be at least experimentally understood better. So having said all of that, the question here is really how to understand quantum nature of gravity. Is gravity quantum mechanical? So we talked about these two theories that are incredibly successful, the best descriptions of nature so far that humans have ever had. And the question is, what happens in domains where they need to be applied at the same time? Does that mean we have to classicalize quantum mechanics? So that would go along the lines of maybe what people who support observers and classical observers would argue. Well, maybe gravity is your ultimate classical observer. Maybe things stop being in quantum states at that time. The other side, which I think I'm more inclined to support, is that actually, no, it means we have to quantize gravity. All of the relevant degrees of freedom, and that's, I think, where space and time now enter, everything that we think captures classically gravity needs to somehow now be converted into these Q numbers. Everything that's a classical number, and in Einstein's relativity, everything is a classical number. You have to now try to think of that as quantum numbers. And the question is, what does that mean? What should I now upgrade from classical to quantum numbers? So you've got approaches to quantum gravity which argue that space and time should be quantized. And there are many approaches of this kind.
That would be things like, I know that as you said there are many, but just to sort of put in context what that means. So for example, you might say that space-time itself comes in almost like little atoms,
Indeed.
For example.
That's exactly what it means.
Okay.
That's right. So people would argue that there is the smallest fundamental length that we can measure. There's the smallest fundamental duration of time that we can measure. No one really knows. We can speculate what they might be. So, these Planck's times and Planck's distances come to mind, but we don't really know. We don't understand that domain very well. So that's one possibility. But another possibility, and that's the one that I'm arguing for, is that what we really need to quantize is the field that leads to gravity. So that you should actually be thinking of gravity not necessarily the way that Einstein originally thought about it and the way that we described it as bending of space and time, which is, I think, how we're traditionally taught this as well.
Yeah.
But we should think of that more like the way we think about the electromagnetic field, that there are various components of the electromagnetic, there are the three magnetic components, and they exist in all places in space and they change in time. But the space-time is more like a convenience grid for us to describe things in a very shorthand manner, if you like. So I can always tell you about the location by pointing to something else. If you ask me, where did you measure that electric field? I could say, it's where that chair is or where that table is. So I never need to give you the full coordinates for that. I can always talk about it relative to something else.
Yeah.
And it seems to me that gravity, that it's much more fruitful to think about quantizing gravity as quantizing these fields, converting these C numbers from Einstein's theory into Q numbers to obey quantum mechanics. And of course, the key question there is, can you test that?
Yes.
And I think that's...
Before we do, again, I want to make sure I've understood correctly.
Yes.
So you're kind of saying that in the classical picture of general relativity, we have this field called space-time and it can bend.
Yes.
You're saying, actually, we don't need that because we already, in quantum mechanics, we have this field which we call the electromagnetic field, which mediates things like magnetism, but all sorts of other things as well, most of the forces that we experience in life.
Yes.
And that field is already described in the language of quantum mechanics. And you're saying we can just use that field instead of space-time?
No, I'm not saying we can use it necessarily instead. I'm saying we should treat gravity in the same way that we are treating electromagnetism. So the way that we quantize electromagnetism, we don't quantize the space-time locations on which these fields sit. We simply quantize the fields.
Okay.
And space-time just remains a classical grid. There's no problem with that.
So it's the Q numbers again, isn't it?
It's always the Q numbers.
That's Q numbers.
That's right. And that's the key thing. As I'm very happy to admit, obviously this may be contradicted by our experiments. So there is no guarantee that this will come out this way, that they will come out as Q numbers.
Yeah.
And it's already extremely exciting that there are so many views. People who agree with this point of view, people who disagree with this point of view, which really tells us that this is something that's exciting to test.
Yeah, I want to talk about the future a bit, but before we do, I just wanted to ask about experiments, because you were just saying, I could be proved wrong. Is there an experiment that could help us probe what you're saying, the ideas that you've just put forward about how we quantize space-time?
Yes, so what I wanted to do in the first instance, and that's the most accessible experiment, is to really show that there are at least some quantum numbers that you need to use for the gravitational field. So even before we understand in detail what exactly needs to be upgraded into Q numbers, I wanted the simplest experiment that would at least force us to acknowledge that some Q numbers must be introduced. Otherwise, we can't model this. It's a bit like Bell's inequalities, that when you violate the Bell's inequality, you know that the state is quantum. You may not necessarily know all the details of your state. You haven't probed all quantum aspects, but you know some aspects are definitely.
You've kind of crossed a threshold.
You crossed the threshold, and I want that kind of threshold experiment. So Chiara Maletto and myself and Sugato Bose independently, we came up with a very simple idea, which is kind of a variant of Schrödinger. I think all experiments ultimately in quantum mechanics are variants of Schrödinger's cat. But you're not doing, of course, you're not involved. No cats involved again. Yeah, that's right. That's right. That's it. So basically, what you want to do is you want to take two sufficiently large objects. Now, I'm saying this from the perspective of atomic physics. They're still tiny.
Sure.
But they are large in the sense that we've never put anything as big as that into a superposition of two different locations. And now you need two objects like that. You need to take one mass, put it in a superposition of two different places, and another mass, and in a superposition of two different places. And now the question is, how does gravity couple these two masses?
Okay, yeah.
Now, is it going to go in the way that I'm advocating, that you're going to have a gravitational force between each of these locations of one particle and each location of the other?
Each of the superpositions.
Exactly.
Yeah.
This is your branching, exactly as Schrödinger envisaged. And this would lead to entanglement between the two masses. And that would be your witness now. If you could violate Bell's inequalities or do any equivalent experiment, you would actually show then that whatever mediates this kind of entanglement must be quantum mechanical. You could show that you cannot do it otherwise. So this experiment is basic in the sense that if you ask me then, but which degrees of freedom are quantum mechanical?
And what do you mean by degrees of freedom?
That's right. So which aspects of the gravitational field are quantum mechanical? Going back to our discussion, is it space or time?
Yes.
Is it the components of the gravitational field? This one wouldn't be sophisticated enough to necessarily answer. Both would be possible.
Okay.
So this would only tell you that gravity certainly has to have some quantum components, and that kind of closes at least that part of it can't be all classical. You can no longer kind of have this dichotomy in the universe. At least some parts of gravity must join this. If you want to know more, I think we would have to get more sophisticated, really, to go in the direction of probing exactly what accounts for this
is much more difficult.
And that's much more difficult.
Yeah. Let's start to come into land and talk about the kind of we talked about experiments that were quite probably many years away. Let's go even further.
Yes.
And in your book, you start to talk about this idea of kind of taking the equations of quantum theory, and you say that there's kind of some unfinished business. I think there's some bits of these equations that aren't really quantum. Yes. And you're saying, well, if we make those quantum, we could sort of have some quite interesting and quite pretty bold predictions.
Yes.
So let's start to explore that a little bit.
Yes, this is, I think, an extremely important question. And actually, the message that I try to emphasize is that that's where the interpretations of your theory are extremely important, because they are your guide as to what kind of questions you want to ask. So if you believe that there is part of the universe that's intrinsically classical, you will never be thinking about experiments that try to engage that bit of the universe in a quantum mechanical way. So even though you could argue, well, at present we can't tell which of these interpretations are kind of correct and which are not maybe a good reflection of reality. That's true at present. However, which interpretation you subscribe to determines exactly what kind of questions you'll be asking. And I think that's where this is important. That's why I'm advocating taking quantum mechanics seriously and going even further down that road.
Yeah. So as an example, again, tell me if I'm getting this right, but like something like the speed of light.
Yes. Yes.
That appears in the equations of quantum mechanics.
Yes.
But it's not a quantum number, it's just a number.
That's right.
299.
Yes, that's right.
However, I can't remember the exact figure.
That's it, meters per second. Yeah, that's it.
But it's just a number, a very big number.
That's it.
So most people wouldn't think like, well, we should quantize that. Most people just think, well, that's just the speed of light.
That's right.
But you're starting to think, well, actually, hold on, what if the speed of light were quantized?
Exactly. I think it's a very important point, because the way we do, it's exactly what we discussed. The way that we come up with quantum mechanical descriptions is we take the equivalent classical description and then we upgrade some of these classical numbers into Q numbers, But then the question immediately comes up, if you really think of everything being quantum mechanical, is what about these other things that we haven't quantized? Why is that the case? Maybe there is a fundamental reason why they ought to stay classical, but if this is the case, then we ought to test it, whether they're also quantum mechanical. So in the full generality, whenever we couple two different fields in quantum mechanics, if you take the field, let's say, of electrons, and you couple it to the electromagnetic field, which accounts for electrodynamics, most of electrodynamics, there is always a bunch of constants that sits in front, which involves things like the speed of light, as you mentioned, where basically it tells you how strongly these two fields couple to one another. And the question is this really just one number? Has the universe really just determined that this ought to be one number? Or what would happen if we also quantize things like that? And I think this is an interesting question, to go fully with this program and really try to come up with a full quantum mechanical description, leaving no places anymore for classical numbers, if you like. Yeah. And the interesting thing is that, yes, this has consequences. What this would suggest is that there are systems which we didn't think of previously as quantum mechanical, which now have to be assigned to this new thing that you upgraded from a C number to a Q number. So it would suggest things like possibly the electrons don't couple directly to the electromagnetic field, but there is an intermediate quantum system which would now arise from this extra quantization, which would actually mediate this kind of coupling.
So the logic here is that, going back to one of the threads that's run through this this conversation, is the idea that Q numbers are, you think, kind of the essence of reality.
Yes.
So what we're saying now is, if we take some constant that appears in the equations of quantum mechanics, and we make it into something that's composed of Q numbers, by definition, those numbers, and we're saying those are the really real thing, they should be able to be entangled with other aspects of reality.
Exactly right.
Okay, so that's where we are, and that's kind of what you're suggesting we probe.
That's right.
Let's come back to our experiment. Does this suggest, could we ever probe that with experimentation?
Yes, I think so, because that's again always goes back to entanglement, which is very interesting. So what you would be probing is the degree of entanglement between the two things that you knew were quantum before, and then the degree of entanglement that you would calculate if this extra quantum system was really there in place. So, and there is in quantum information, there is something that we call monogamy of entanglement. And monogamy of entanglement means the following thing. If two things are really maximally entangled, that means that neither can be entangled to anything else.
Okay.
And that's what you are testing.
Yeah.
So in the former theory, it would say the electron gets fully entangled with the electromagnetic. There's nothing else in this connection. If there is an extra quantum system, you would see reduced entanglement between the original two systems because of the presence of the third system.
Yes.
So these are the kind of things we should be looking for.
So you would infer it from that?
Infer it indirectly.
You would see less entanglement than you expect.
That's right.
Yeah.
So it doesn't necessarily mean that you would have to directly detect the quanta of this. No. It could be that there are quanta of this extra system, and maybe you can detect them. But even if you couldn't, you could indirectly infer the existence of this extra system.
And what would that look like if the speed of light was quantized?
Yes.
What does that, my head slightly explodes, like what does that mean? Does that mean there's some extra field? I don't quite understand.
Yes, that's right. There would be extra field, and that would be associated with this. Like I said, there could be quanta of this. It would also force us then to understand why, for all our practical purposes so far, we can get away with only a single number. Because the first question you should be asking is, could I then come up with situations where I would get these other speeds to be relevant and so on?
I just want to touch on, I don't know if I dare open this can of worms, but what about time? Could one apply that logic, like we were talking about, quantizing something like the speed of light? Could consider time in that way, and what implications would
Yes,
that have?
I think that's one of the chapters in the book even explores that separately, even without going into the full general relativity. You can do experiments with time separately, and I think that's also mind-blowing. So you could actually test this idea that time flows at different rates for different observers. If the observers are moving at different speeds, as Einstein said, they would perceive time differently. You can actually now take a single particle, a single atom, you make it into a superposition of two different places. And in one of these places, you take it on a journey and back. This would be like the twin paradox that Einstein called it. But of course, he did it with two twins. Here, you are really doing it with a single quantum system. But it's just in one branch of this superposition, you take the atom on this journey and bring it back. And when you bring it back, you've got still one and the same atom, but it shows two different times because of quantum mechanics. And that sounds, no one has done this experiment.
No. Yeah.
And I think it's doable, and it seems to me an immediate consequence of quantum mechanics as well.
What would it mean for the particle?
That's right.
I can't even wrap my head around it. It would mean that the particle somehow has two times.
Yes, and this beautifully, indeed, and this goes back to this thing that different observers, if you want to call them again, can ascribe different properties to one and the same system. So in one branch, you've got one time, it's superposed with there's a younger version of the particle and older version simultaneously sitting in the same location. And the person doing the experiment has their own clock. There is yet another time in the laboratory, which is equally good for that purpose as well, but it's different to the other two times as well. So there are these multiple perspectives that all exist simultaneously within quantum mechanics. And I don't see any reason why the same shouldn't be true for time.
So we've covered a lot of ground. We started with observers, we've talked about particles, space and time. We've even talked about two particles having two different times, which I'm still not completely sure I understand. But I guess just to wrap up, we've also talked about a lot of experiments that you have proposed.
Yes.
What I wanted to get you to do as we close, Vlatko, is like imagine that perhaps it's 10 years in the future. You know, your book has sold really well. Physicists have embraced these experiments, and we've done all of them. And let's imagine that they've all worked out exactly as you think they will. It's all gone your way.
Yes.
How does that change our picture of reality? Because your book is called Portals to a New Reality. Paint me a picture of what that new reality would look like if it all goes as you think it will.
Yes, I think that's the key question. Again, that's what all of us in physics would really like to understand ultimately. So I think if these experiments came out the way that I'm predicting, that would really tell us that we should be thinking about unifying our two key theories, general relativity and quantum mechanics, in a very specific way, which is the one that I'm advocating, which is to upgrade these classical properties in general relativity to these quantum numbers. Again, the experiments that I suggest only take us a certain way. As I said, there will still be a lot of open questions there. How far should we go down that road? So the other extreme, for instance, which I don't really discuss much, are the very, very strongly gravitating systems like black holes, for instance. So that's the one where gravity is so strong that it certainly could be that there are new effects coming out of there when you merge it with quantum mechanics. So the experiments I have in mind are really lab-based, and they involve relatively weak gravitational. So that would be like the first order corrections to Einstein's theory. So certainly if they were confirmed, I think it would tell us that we need to probe more of these properties and see how far this goes. Is it really true that the whole of general relativity needs to really be quantized ultimately, which is one possibility. And that theory may be a completely different theory in the sense that it may give us quantum mechanics and general relativity as two special limiting cases of this theory, but in fact it could be a much larger theory predicting completely new phenomena.
Yeah. So it would in a sense put us on a new path.
That's it.
But we don't quite know where that path's going to end up.
Yes,
yeah.
I think it's very similar with any revolution that we had in physics, a bit like with quantum mechanics, that with Max Planck, we knew that we needed to discretize energy in order to explain black body, but he couldn't quite anticipate how far this would go, that it would spread to atomic structure and everything else, really, ultimately.
Vlatko, thank you so much for talking to me. We've covered a lot of ground. I think I probably need a cup of coffee after that, but it's been an absolute pleasure.
Thanks very much, George.
Thank you so much. Thank you.
Pleasure.
Yeah.